Hello, this is my English speaking practice, and I'm talking about my tech study. Yeah, and today I'm going to study about system design. I found this website. This seems to be good. This seems good. Yeah. Yeah, it's well organized and it's free. It's for free. Yeah. hellointerview.com. And today I'm going to read this article, introduction, because I'm interested in system design. Yeah. Right now I work as engineer, system engineer, and I usually work on infrastructure on cloud. But if I develop my career, I need to learn about system design and stuff. So this is good for me. So I work on this. Yeah. So introduction, learn system design first. But I want to set a purpose or goal. Yeah, because I want to not only speaking practice, but also learn something. Yeah. So but anyway, I will read this. So while conducting thousands of mock study design interviews with Hello Interview, we frequently work with candidates who have an upcoming interview in a few days or even tomorrow. Let's be real. No one is going to become a system design master overnight. Instead, what we put together is system design in a hurry, using data from hundreds of mock interview sessions across companies and interviewers. We've identified the most common flags and outlined the content to help you eliminate them. Wherever possible, we link to in-depth information should you wish to learn more. The intent here is to cover the last and most impactful 20%, not to teach you from scratch. While system design in a hurry won't build mastery, it's still high leverage. The key concepts we cover are relevant for system design in the real world, and interviewers generally will try to align their interviews with these concepts because they are practical, not strictly academic. Other system design materials are either ChatGPT spew or go to a level of depth that you'll never possibly cover in an interview. Might be yellow flag if you do. We aimed to make system design in a hurry dense, practical, and efficient. Moreover, it's 100% free forever. While we could charge for this material, we think it's far more important to level the playing field of system design interviews. If you want to support us, we have supplementary content available by our premium offering, and our expert interviewers are available for mock interviews and can pinpoint the primary areas for you to focus much better than any guide can. Okay. If when I will get better in my English, I want to take this mock interview in English. Okay. So, how to use this guide? So this content is for free forever, and it's dense. They say this is dense content, and overall structure is like this: core concept, key technology and patterns, design framework, and practice common problems. At a high level, preparing for system design interviews is really about assembling the right pieces. You will need to know some core concept, key technologies, and common patterns. On this base, you will establish a strategy or delivery framework for executing the interview. And finally, you will need to practice to ensure you are comfortable the day of your actual interview. For more experienced candidates, this may be just organizing things you already know to be ready for your interview. For others, you may need to do some deep dives to learn more about relevant topics so you are prepared for the detailed questions from your interviewer. For your preparation, we recommended that you read this guide in order, skipping any sections you already know. Okay. While you link off to additional material where relevant, we've tried to make things guide as self-contained as possible. Don't worry if you don't have time to read additional materials. Throughout this, the guide we've layered in commentary in these tips and warnings for common mistakes or things people tend to overlook in the interview. Pay attention to these, as they are the most likely things to end up as yellow flags in your interview. Okay. If you are really short on time, we recommend covering the delivery framework section, skimming the key technologies, and spending any remaining time study the core concept section. But I have some time, so I will go with in order. Types of system design interviews. Each company and sometimes each interviewer will conduct a system design interview a little differently. Often the differences are not important, and you can prepare for all of them with the same material, but some interview types require different preparation. Okay. 4 types of software design interviews: infrastructure, product design, front-end design, OOP design, object-oriented programming design, object-oriented programming is okay, I see. Product design interviews, sometimes called product architecture interviews, or ambiguously system design interviews, are the most common type of system design interview. In these interviews, you will be asked to design a system behind a product. For example, you might be asked to design the backend for chat application or the backend for ride-sharing application. Often, these interviews are described in terms of a use case. For example, design the backend for a chat application that supports one-on-one and group chats, and frequently referred to by the most noteworthy company. Noteworthy. objective meaning worthy of attention, noteworthy, and frequently referred to by the most noteworthy company that uses that use case. For example, design the backend for a chat application like Slack. This guide will be useful for product design interviews. Example questions is design a ride-sharing service like Uber. Design chat application like Slack. Design social network like Facebook. Okay. And infrastructure design. Infrastructure design interviews are less common than product design interviews, but still relatively common. In these interviews, you will be asked to design a system that supports a particular infrastructure use case. For example, you might be asked to design a message broker or a rate limiter. Since these interviews are deeper in the stack, your interviewer will be looking for more emphasis or system level mastery. Example, consensus algorithm, durability considerations than high level design. Okay, I'm more interested in infrastructure design. Like this, yeah. And object-oriented design. Okay, object-oriented design, sometimes called low-level design interviews, are less common than product design interviews, but still occur at companies that use a object-oriented language like Java. Amazon is notable for these interviews. In these interviews, you will be asked to design a system that supports a particular use case, but the emphasis on the interview is assembling the correct class structure, adhering to solid principles. Single responsibility. What is O? L is risk of replacement method. I is interface segregation. D is dependency in inversion principles. O is I forgot O. What does O stands for? Coming up with a sensitive entity design, etc. For example, you might be asked to design a parking lot reservation system or a vending machine. But rather than breaking this problem down into services and describing the backend database you are instead asked to describe the class structure of a solution. Okay. This guide is not as useful for object-oriented design interview. We instead recommend grokking the low-level design. This is another. What about this? Educative. Popular roadmap and learning guides. AWS. I didn't know that. Explorer. For some languages and frameworks. Okay, anyway. Where I left off. Okay, example questions: design a parking lot reservation system, design a vending machine, design an elevator. I see. So this site focus on product design and infrastructure design. Okay, so I will skip regarding front end design and interview assessment. Yeah, this is not for now. Okay. Problem navigation. Your interview is looking to assess your ability to. Okay. Technical. Okay. So I want to know about core concept and key technologies, or like that. So core concept. Let's start with core concept. While understanding the common structure for your interview in delivery will help you pilot your interview, it won't be sufficient for you to solve the problem you will encounter in the interview. For this, you'll need to understand some core concepts of system design. Yeah, of course. Below are the most common concepts you'll encounter in a system design. So let's see the table. Scaling and CAP theorem, locking, indexing, communication protocols, security, monitoring. Nice. So the first one is scaling. One of the most important topics in many system design questions is how to deal with scale. So while there are a lot of ways to do this, your interviewer is definitely going to want you to know how to scale a system horizontally. Horizontal scaling is all about adding more machines to a system to increase your capacity. This is in contrast to vertical scaling, which is the process of adding more resources to a single machine to increase its capacity. Yeah, this is common sense. And more senior interviewers will recognize that vertical scaling actually requires significantly less incremental complexity. If you can estimate your workload and determine that you can scale vertically for the foreseeable futures, this is often a better solution than horizontal scaling. Many systems can scale vertically to a surprising degree. I see. Yeah. So if you can predict the workload, amount of traffic, it's recommended to scale vertically because that is less complicated than horizontal one. Because horizontal scaling needs some like load balancer or like that, but the vertical scaling just enforcing server, so it's simple, so it's preferred if it's possible. And inexperienced candidates tend to do more mistakes. They leap to horizontal scaling to solve any performance problem, even when it's not necessary, and they don't consider the implications of horizontal scaling on the rest of the system. When you encounter scaling bottleneck, make sure you are not throwing machines at a poor design. Rest of the system, they don't consider the implications of horizontal scaling on the rest of the system. Doesn't make sense. implications on the rest of the system. I see, I understand. Okay, so the horizontal scaling might affect rest of the system, and when horizontal scaling is the right solution, you will need to consider how to distribute work across your machines. Most modern systems use a technique called consistent hashing to distribute work across a set of the machines. This is a technique that arranges both data and machines in a circular space called a hash ring, allowing you to add or remove machines with minimum data distribution. Yeah, consistent hashing. Yeah, which is what I've learned here. Yeah, I learned about consistent hashing. Consistent hashing is a technique for distributing keys across servers in a scalable way. It's widely used in distributed databases and key value stores. The idea is to avoid the inefficiency of the simple modulo approach. With modulo, if you add or remove a server, almost all keys need to be reassigned, which is very costly. So consistent hashing solves this by organizing servers in a ring and assigning keys to the nearest server in the ring. This way, when servers are added or removed, only a small fraction of keys need to be moved. That makes it very efficient for dynamic distributed systems. So consistent hashing works by mapping both server nodes and keys onto a ring using hash functions. Each key is assigned to the first server in the clockwise direction, and when a new node is added, it's placed on the ring, and only the keys that fall between the new node and the previous node are reassigned. This minimizes the amount of remapping, which is a main advantage over simple modulo hashing. Yeah. Okay. Work distribution. The first challenge of horizontal scaling is getting the work to the right machine. This is often done by a load balancer, which will choose which node from a group. By a load balancer, which will choose which node from a group to use for incoming request. Which node from a group will choose which node from a group to use for incoming request. While load balancers often come with many different strategies, least connections, utilization based, etc. Simple round robin allocation is often sufficient for asynchronous jobs work. This is often done by a queuing system. Asynchronous job work. This is often by a queuing system. Makes sense. Okay. And work distribution needs to try to keep load on the system as even as possible. Okay, for example, if you are using a hash map to distribute work across a set of nodes, you might find that one node is getting this property proportionate amount of work because of the distribution of incoming requests? Yes. Yeah, that could be. Yeah, the scalability of your system ultimately depends on how effectively you can remediate this. If one node is 90% busy and the remaining 10% busy, you are not getting much out of your horizontal scaling. Yes, so the distributing equally is so important. Data distribution. You will also need to consider how to distribute data across the system. For some systems, this implies keeping data in memory on the node that's processing the request. This implies keeping data in memory on node. You'll also need to consider how to distribute data across the system. For some systems, this implies keeping data in memory on the node that's processing. So you will need to also. I understand the English, but I don't get the meaning. More fluently. This implies keeping data in a database that's shared across all nodes. Look for ways to partition your data such that a single node that can access the data it needs without needing to talk to another node. If you do need to talk to other nodes, a concept known as fan out, keep the number small. Okay. A common anti-pattern is to have requests which fan out to many different nodes, and then the results are all gathered together. This is scatter-gather pattern. Can be problematic because it can lead to a lot of network traffic. It's sensitive to failures in each connection and suffers from tail latency issues. If the final result is dependent on every response. Okay, I understand the second part or part. Later part.
I understood the latter part.
Latter part.
I understood the latter part.
Latter part. Latter.
Ladder.
Latter. Oh. I used these words for the first time. Latter part. But the latter part. What is the opposite? Former? No. Former. having previously tension. Okay, former. Latter, former, latter, former, latter, former, latter. You will also need to consider how to distribute data across the system. For some systems, this implies keep data in memory on the node that's processing against. More fluently, this implies keep data in a database that's shared across nodes. Okay, so I should consider how to distribute data across the system, and for many cases this means to keep data in memory on the node that's processing the request. Why? I don't know the logic. And more fluently, so in other words, so this implies keeping data in the database that's shared across all nodes. Look for ways to partition your data. So I need to partition my data. Yeah, because a single node can cross the data it needs without needing to talk another node. So I should reduce the amount of communication over network for nodes, all of nodes. So so talking to other nodes we call fan out. So we should avoid fan out as much as possible. Okay, so this is a common anti-pattern. So in order to do that, we use database to keep data, because it can share across all data. Okay. But I still don't understand the logic about this, because I understand how to distribute the data. So I imagined like a load balancer or like that. So it's distributing the data. I see. I understand. I get it. What you want to tell. Okay. So if you can use a database, that is good, because that can share across all nodes. So we can remove fan out completely. Okay. Maybe. Okay. So if your system design problem involves geography, there is a good chance you have the option to partition by some sort of region ID. For many systems that involve physical locations, this is a great way to scalable. Because for many problems, a given user will only be concerned with data in or around a particular location. For example, a user in the US doesn't need to know about the data in Europe. So we can partition data by region ID. Okay. Inherently, Inherently is an verb that means something exists as a natural. Inherently. Uh-huh. Inherently. Horizontal scaling on data introduces synchronization challenges. You're either reading and writing data to a shared database, which is a network hop away, 1 to 10 milliseconds ideally, or you'll keep multiple redundant copies across each of your servers. Redundant copies. Yeah, this means race conditions and consistency challenges. Most database systems are built to resolve some of these problems directly. Yeah, by using transactions. Yeah, in other cases, you may need to use a distributed lock. Regardless, you will need to be prepared to discuss how you are going to keep your data consistent. Yes, I think this problem is important and challenging. Yeah, so here is cap theorem. Cap theorem is a fundamental concept in distributed systems that states you can only have 2 or 3 properties: consistency, availability, and partition tolerance. In practice, since network partitions are unavoidable, this means choosing between consistency and availability. Yes, exactly. Choosing consistency means that all nodes in your system will see the same data at the same time when a write occurs, or subsequent reads will return that value. Sorry. Choosing consistency means that all nodes in your system will see the same data at the same time. Yes. When a write occurs, all subsequent reads will return that value, regardless of which node they hit. I see. However, during a network partition, some nodes may become unavailable to maintain this consistency guarantee. Yes. So it discards availability for consistency. Yeah. On the other hand, opting for availability means that every request will receive a response, even during network partitions. The trade-off is that different nodes may temporarily have different versions of data, leading to inconsistency. The system will eventually reconcile these differences, but there is no guarantee about when this will happen. Okay. So in a system design interview, availability should be your default choice. I see. You only need strong consistency in system where reading stale data is unacceptable. Stale data. Examples of systems that require strong consistency include inventory management systems where stock levels need to be precisely tracked to avoid overselling products. Booking systems for limited resources, airline seats, event tickets, hotel rooms, where you need to prevent double booking. Banking systems where the balance of an account must be consistent across all nodes to prevent fraud. The key characteristic of these systems is that any inconsistency, even temporary, could lead to significant business or technical problems. Okay. Gotcha. don't feel pressure to choose a single consistency model for your entire system. Different features often have different requirements. In an e-commerce system, product descriptions can be eventually consistent, while inventory counts and order processing need strong consistency to prevent overselling. So in this case, it requires strong consistency. Yeah. And locking. Okay, locking. In our system, but okay. I should practice speaking. Just reading is not good. So what I learned today: scaling, but okay, so I have to summarize. Hi, I've learned about system design today, and especially core concepts. And first, I've learned about scaling, and yeah, there are two types of scaling: vertical and horizontal. Horizontal scaling is to increase the number of computers, and vertical scaling is to enforce or upgrade computer. Yeah, so I have to choose from them properly, based on the situations. If we can predict the amount of traffic, the vertical one is recommended because that is more simple than horizontal one. But in many cases, we cannot predict the amount of traffic, so we choose horizontal scaling. Horizontal scaling requires something to distribute or routing traffic to proper servers. Yeah. And distributing and routing is also important because if you increase the number of servers, it doesn't make sense when the distribution is not good. And yeah, that is about work distribution. And there is another type of distribution we called data distribution. Data distribution means how you store the data across the systems. So when you choose the horizontal scaling, the servers increased. So sometimes we need to communicate. The server needs to communicate with other servers, right? Yeah, but it makes it complicated, so you should reduce the amount of communication between servers as much as possible. Yes, so you can use in-memory data store or databases. And also you partition your data, and you might need to synchronize data across all of servers. So you should take it into consideration. And next topic is CAP theorem. CAP theorem. CAP theorem is theory. It says you can choose 2 of 3 properties from availability, consistency, and partition tolerance. And for real world, you cannot avoid the partition failure. So you end up with choosing availability or consistency. And in many cases, you will choose availability, and but yeah, there is a situation you have to choose consistency. So the situation requires strong consistency. Systems such like banking systems, inventory systems, and reservation systems for small amount of resources. Yeah, that's it. Okay. Hi, today I learned about system design, especially some core concepts. I studied scaling, and there are 2 types: vertical scaling and horizontal scaling. Horizontal scaling means increasing the number of computers. Vertical scaling means upgrading or strengthen a single computer. We need to choose between them depending on the situation. If you can predict the amount of traffic, vertical scaling is recommended because it's simpler than horizontal scaling. But in many cases, we cannot predict the traffic, so we use horizontal scaling. Horizontal scaling requires some kinds of distribution or routing to send requests to the proper server. Distribution and routing are important because just increasing the number of servers doesn't help if requests are not distributed properly. There are two kinds of distribution: work distribution and data distribution. Work distribution means spreading the incoming requests across servers. Data distribution means storing data across multiple systems. When you use horizontal scaling, the number of servers increases, and sometimes servers need to communicate with each other. This makes the system more complicated, so we should reduce inter-server communication as much as possible. To help with this, you can use in-memory data stores or databases. You can also partition your data, but sometimes you need to synchronize data across all servers. So you need to take these trade-offs into consideration. The next topic is the CAP theorem. The theory says you can choose 2 out of 3 properties. 2 out of 3 properties: availability, consistency, and partition tolerance. In the real world, you cannot avoid partition failures, so you always end up choosing between availability and consistency. In many cases, you will need availability, but in some situations you must choose consistency. For example, banking systems, inventory systems, or reservation systems with limited resources. That's it. Yes. Okay. That's it. I will go with, I will continue from locking tomorrow. Thank you for watching. Bye.